Okay, well today we're going to resume our discussion on chapter 15. We just had maybe one more example, and then we're going to forge ahead into chapter 16. We should get through that. I hope you have those notes with you as well. We'll get to chapter 18 on Friday, and I'll send those notes out to you guys later today. So maybe hopefully you have enough time to get those printed. But remember, in chapter 15 here, we're talking about tests of significance or hypothesis tests. So in chapter 14, we talked about using a confidence interval to estimate something, estimate the population mean. And here we're going to do something similar, but instead of providing an estimate of the population mean, we're going to do a test where we're going to say either this one thing is true about the mean, it's equal to something, or something else is true. And so, again, this is going to be a formal way to assess the evidence in some way about the two claims that we have going. And so, just maybe to remind you here that the kind of the main things that we're talking about in this after we get our hypotheses set up, which we'll practice again here in a second. We have our test statistic, and then we find calculate a p-value, and then we either reject or we fail to reject the null hypothesis, and kind of talking about how to interpret that appropriately. So in this chapter, remember the null hypothesis is always going to be that the population mean. So remember, this is the population mean, and this mu0 is a hypothesized value. So we're throwing some more subscripts at you here. We have x bar, y hat. Now we have mu0. Just remember that is to represent what we're hypothesizing as a possible value for that population mean. Then the test statistic we're going to use to test this hypothesis is kind of the usual thing that we've seen before, except that we're throwing in a mu0 there in the numerator instead of mu. So we take the average that you get from your sample, subtract off the hypothesized mean, and divide by the standard deviation, which is sigma divided by the square root of the sample size. So that's our test statistic. And just reminding you, the null hypothesis is always going to be in this chapter anyway, that mu is equal to mu0, whatever we hypothesize there. And then we have sort of three choices for our alternative hypothesis. Either we want to see if it's greater than that value, that hypothesized value, less than, or simply different from, or not equal to. So just reminding you, that's kind of the way we're setting up our alternative hypotheses. And the p-value that we're going to calculate here, so the p-value for this hypothesis is going to be that capital Z is greater than little z, which is our test statistic. If your alternative hypothesis is the other way around, it's going to be less than your test statistic, and if it's simply not equal to, then we're going to take 2 times the probability that it's less than whatever our test statistic is there. So if you're confused about how we're finding our p-value, you can kind of match up the inequality sign from the alternative hypothesis in your probability statement there, and that's going to be the way that we're finding what our p-value is. So again, we looked at an example. We're going to do it one more today, and kind of going back and hitting all these things again. And actually, let's review that real quick. So if you remember, the last thing we did in class on Friday, the next to last example in your notes was this screen time example, and we're interested in comparing a Gavin, which is our cousin. Imagine that we want to see if his screen time is different from what we found to be true for other students, which was 6.1 hours per day. And so we set up our hypotheses. Again, our null hypothesis is that mu, which is Gavin's average daily screen time, was equal to everybody else, 6.1 hours. And here our alternative was just that we want to see if it's different than everybody else. So just kind of reviewing what we did last time, stepping through it. This is nothing new just yet. So then moving on to the solve step of this thing, we had to check our conditions. We wanted to make sure that because we were not told that the population is normal, we don't know what the screen time, the distribution of screen time is for all children under 12. We wanted to check our conditions, the random sample, small enough, large enough. Those did all check out, and so we were able to proceed with our calculations. We calculated our test statistic, got a 3.04 there. And then because our alternative hypothesis was that that mu is not equal to 6.1, we took our p-value to be both of those tail probabilities, so 2 times the probability that it's bigger than 3.04. So we calculated what our p-value was. We got down to the bottom, that red box, and we compared it to our significance level, which is here is the usual 0.05. Because the p-value was smaller than that, we rejected the null hypothesis, which caused us to conclude kind of a formal interpretation of what it means to reject the null hypothesis was that we have sufficient evidence to conclude that Gavin's average daily screen time is different from that of other children under 12. So that's kind of what the alternative hypothesis says. Again, the alternative said that mu was not equal to 6.1. And so what we're saying is that we're going with that one, is sort of the informal way of saying it, but to formally say that we do have enough evidence to say that this down here is true now. So just some review here. Any questions on kind of the procedure or what we're doing here, or anything like that? We're gonna do one more example here. But before we, one more thing before I move into that last example. So again, the question that I wanted to pose to you here is why is it important to set the significance level before the test has been done? So again, remember the significance level is alpha. So that's what we're comparing our p-value to make our decision. So we're going to either accept or we're going to reject or fail to reject the null hypothesis based on whether our p-value is smaller than or not, or smaller than or greater than the significance level. So can you guys think of why it's important to set what this alpha is before we do the test rather than sort of after we've done all our calculations? Well, let's suppose that that the p-value for whatever our example was something like 0.02. So suppose my p-value is 0.02. So if alpha is equal to 0.05, then I reject the null hypothesis. But if alpha is equal to 0.01, now my p-value is not smaller than alpha, and so I will fail to reject. So if I do all my calculations, see what my p-value is, and then set my significance level, I can get whatever decision I want there, if the p-value is pretty small anyway. So it's always important to sort of, before you go into the calculations, kind of think about what a good significance level is. Usually 0.05 is the way to go, but just a point that it's very important to set alpha before you do the test. All right. So the next to last page of your notes has kind of a blank template there, which is something that can be very helpful as we're going through these conducting these hypothesis tests, and kind of reminding you again that the important steps in any process here is that we want to kind of state the problem, we want to give what our plan is for solving that problem, actually solve that problem, and then give a conclusion. So Dr. Baker put that together to kind of give you an outline as you were working on your homework problems or whatnot, to be able to kind of follow that through and give you some steps on how to do these problems. So just quickly stepping through these, the state part of the process in this chapter is that we want to think about what is the practical question that we're going for here. And so we can sort of state the question verbally, kind of restating what's given in the problem. And Dr. Baker threw that mathematical statement in the first step. I would actually suggest putting it in the plan step, because you can identify what your parameter is and then kind of translate the words into symbols and state it mathematically. You can list the information that you've been given. What's the sample mean? What's the sample size? What's the population standard deviation? All of those good things. Figure out what my hypotheses are. Say what my level of significance is, and then kind of determine what type of test I have, if it's one-sided or two-sided. If a picture helps you, kind of sketching out what an unlikely test statistic would be, all within the plan step. And then to actually solve them again, we need to first make sure that we're allowed to use these formulas that we have. So first we need to check our conditions. So if the population is not normal, then we have our few conditions to check there. Then we can go ahead and, if those check out, we can go ahead and calculate the test statistic, find the p-value, and then finally conclude, which means either reject the null hypothesis or fail to reject the null hypothesis, and then write a statement to interpret the decision in the context. So saying something like, there is enough evidence or there is not enough evidence to conclude that whatever our conclusion is, and then say what the significance level is. So lots of steps there, lots of things to fill in. You don't have to go through that every time. It is just kind of a way, as you're getting started with these, to kind of practice what exactly we need to do when we're solving these problems. So for this last example, I do want to kind of step through this and show how this can be kind of helpful in kind of really pulling out all the information that we need. So we should be on to the last page of your notes now, this final example. All right, so the example here says that we're looking at IQ scores now again, and we know that they follow a normal distribution with population standard deviation sigma equals 15. So we suspect that persons from affluent communities or wealthy communities have a above average IQ scores, and so we want to kind of see if that's true. So we take a random sample of 35 residents from an affluent community and find that they have an average IQ score of 112. So is there significant evidence to support our claim at the alpha equals 0.05 level? All right, so keeping that in mind, the first step in our process here is to kind of state the problem. So this problem is a little bit more vague as to what the actual question is. It doesn't say conduct a hypothesis test and find whatever. So this is maybe a good example of why this is helpful. So what is the practical question that requires a statistical test here? We're going to start out just saying what it is verbally. So can anybody give me a hand? What's the question that I'm trying to answer here? Just in words. So sort of what's the question? Just in words, what am I interested in finding out here? Yeah, Elisa.
If average IQ scores are higher for those people of the population in affluent communities.
Absolutely, yeah. Our average IQ scores our average IQ score is higher in the affluent or wealthy So again, just kind of taking again what the example says. I suspect that this is maybe the case. So the question that I sort of want to answer is: our average IQ score is higher in affluent or wealthy communities. Very good. Does everybody see where we got? I mean, that's kind of just pulling out what we have in the question to say what's the actual question that we're interested in here. Okay, so that's sort of, again, the problem doesn't tell us exactly what question, and so if we can pull that out, that's kind of our first step, stating the problem verbally there. So here in our plan step, again, the first thing we can do is to identify the parameter. So here, we're looking at mu. So what is the parameter that I'm interested in testing here? Kind of going from what we just said in our sort of restatement of the problem. Average IQ scores, and specifically which average IQ scores? So you're very close. So average IQ scores of what group of people? From the affluent communities. So again, so we're interested in the average IQ scores but again, remember sort of the population parameter. What we're really trying to say about the larger group is that we want to know about the average IQ scores from the affluent communities. So So again, the thing that we're trying to say something about is mu, which in this case is the average IQ score from affluent communities. So overall, everybody who lives in an affluent community, if we took all of those people, what's their average IQ score? So before we go on, I need to jump back. I realized I left something out here. So what we saw before is that these IQ scores follow a normal distribution with mean equals to 100. So population distance. So overall, everybody, not just the affluent communities, those IQ scores have a normal distribution with mean 100 and standard deviation sigma equals 15. So forgot to throw that in there. That was being left out. So maybe I'll tack one other thing on here to our verbal statement of the question. So our average IQ score is higher in affluent communities. Maybe we'll throw in than in the population. So again, what we want to compare affluent and wealthy communities to is the population as a whole. So again, maybe I'll tack that on there. Maybe that was sort of goes without saying, but we want to see, are these IQ scores in the affluent communities higher than they are in sort of the whole population. So now we know what mu is. Now we can put out what our hypotheses are here. So again, our null hypothesis is always going to be that mu is equal to something, and our alternative is going to be that mu and then some inequality sign and then the same number. So the same number will go here and here, and then we just need to figure out what that number is and what the inequality and the alternative hypothesis is. So what is my hypothesized value? So what am I checking this IQ scores for affluent communities? What am I checking that against? I'm checking it against the whole population. I want to see how this sort of subgroup compares to the population as a whole. So what would my hypothesized mean be? Yeah.
Did you say the average score is equal to the average score of the population?
Yes, exactly right. And so that is the 100. Yeah. So again, we wanted to compare. Remember, our question of interest says, are these average IQ scores higher than in affluent communities than the rest of the population? So we want to see if our average IQ for the wealthy communities is the same as the rest of the population, or if it's higher. So we want to compare mu to 100, which is the population number. So we can put that same 100 over here. And then what inequality sign do I want to put in my alternative hypothesis? Less than, greater than, or not equal to? Greater than, right? Because my question here says our average IQ score is higher. So I don't care if they're lower. I just want to see if they are higher. So I'm going to put that mu is greater than 100. So again, this is kind of the normal way to attack these problems. So the alternative, the null hypothesis will always say that there is no difference, that my mu, whatever I'm looking at here, is equal to whatever I'm hypothesizing it to be, which is here would be the rest of the population. The alternative hypothesis kind of says, no, it's not equal to. It's actually bigger than. That's kind of what I'm interested in finding out. And so I'm going to go do this hypothesis test and then make a decision at the end of which one of these two things is true. Is that okay with everybody, how we set these up? All right. Well, maybe I guess in our steps this was actually C, wasn't it? In B, we can list out all the information that we have. So we know what our sample size is. We know what our sample average is. We can find out what sigma is equal to. And then we can also say what, well, let's just maybe reiterate what the hypothesized value is, and then what our significance level is equal to. So going back to the example and kind of pulling out the important information, the number of people I have in my sample is those 35 residents. The average I get from that sample is 112. We're told the population has a sigma of 15, and we know that we're hypothesizing that mu 0 is the 100. That's which is the mean from the population as a whole. So then finally, what's my significance level that I have here? 0.05, exactly right. And that's again just pulling that right out of at the alpha equals 0.05 level. All right, so we've kind of picked out what the parameter is that we're looking at here. We've stated our hypotheses, and we kind of have all the information that we need. Before we can jump into using our calculations, our formulas, again, we want to make sure that it's okay to use those formulas, which again always involves checking our conditions. So what do we? Well, we're told something about the population in this case, right? We're told that that follows a normal distribution. So our population is indeed normal. But let's go ahead and just write out what our conditions are anyway, and kind of make sure that we're in a good boat here. So first of all, do we have a random sample? Do we have a small enough sample? And is it large enough? So thinking about, do we have a random sample in this example? Well, that's the usual answer, yes. It's stated in the problem. Small enough, 20 times n is 20 times 35, which is 700. Which is less than all affluent households. So our sample is indeed small enough. And is our sample large enough? Well, we have n is equal to 35, which is less than 40. 40 is sort of our usual cutoff. But this is not going to be a problem. But it's not a problem because the population is normal. So maybe just for good practice, kind of always write out what all three of the conditions are, and because we do always want to make sure we have a random sample, that's always important. But if the population is normal, then that large enough condition is not really important. So because we have a normal population, we're okay to proceed. We're okay to proceed here. All right. So the next step here is to calculate our test statistic. And again, hopefully you can see this. Again, z is equal to, again, because our conditions checked out, we're okay to move on here. Z equals x bar minus mu 0 over sigma divided by the square root of n. Again, we can just fill that information in from what we picked out on the previous slide. So 112 minus 100 divided by 15 divided by square root of 35, which is equal to 4.73. So once we have our test statistic, if everyone's okay with that, then we are ready to find our p-value. So again, remember, let's z equals 4.73. So our p-value is going to be equal to the probability that a standard normal is bigger than 4.73. And remember, I get this because the alternative hypothesis was that mu was greater than 100. So the alternative said that mu was greater than 100, so the p-value is going to be that z is bigger than 4.73. So kind of following that there, and again, this is just equal to 1 minus the probability that z is less than 4.73, which is approximately equal to 1 minus 1 or 0. This p-value is essentially 0. We could say it's 0.000000001 or something like that, but for all practical purposes, the p-value is pretty much 0. Yeah.
Where do you get the probability that z is less than 4.73 is equal to 1?
Oh yes. So again, remember we're talking about the standard normal distribution here. So this is our z down here, centered at 0. If this is 4.73, what I really want is this area up there, but let's see, this right here would correspond to this area that's being less than 4.73. Again, so you go to the table, you look up 4.73, but you can't because it's not there. The biggest number in the table is like 3.49 or something like that. So what we know from the table that 3.49, the area down here is like 0.9999 or something like that. So if we go out further than that, the area is going to be 0.999999 or something bigger than 0.9999. So what I'm saying is that the area less than 4.73 is pretty much 1. Very good question. And as we're doing hypothesis tests, you'll more often see that we have test statistics that are outside the range of the table. So again, if you get a number that's bigger than something that you have on the table, the area above that is pretty much 0. If you get an area that's off the end of the table on the negative side, the area below that's pretty much 0. So kind of getting familiar with that idea will be helpful for you. Very good question. Okay, so again, what we've done, we figured out all of our information. We wrote our hypotheses. We checked our conditions. We calculated our test statistic. Now we're ready to make a decision. So again, let's write that our p-value is essentially 0. So that squiggly equal sign means approximately. And so, again, what I want to do with my p-value is I want to compare that to my significance level. So remember that that alpha is equal to 0.05. So, of course, the p-value here is less than p-value is less than my significance level of 0.05. So what does that mean? Am I going to reject the null hypothesis, or am I going to fail to reject? Absolutely, reject. Remember, when the p-value is less than alpha, we're going to reject. We're going to reject the null hypothesis. So that's our decision. We've decided to reject the null hypothesis because our p-value was less than 0.05. So to finish this up, we just need to kind of say what that means, right? Again, what does rejecting the null hypothesis means? Well, let's put that in words. So what we can say is that because we've rejected, we can say that there is sufficient evidence that the average IQ score in affluent communities is higher than the population as a whole. At a significance level of 0.05. So again, what we can say is that there is sufficient evidence that the average IQ score in affluent communities, which is, again, that's our mu, is higher than the population as a whole, which is 100. So we've rejected the null hypothesis, kind of think about we're going with the alternative, and then we just want to say what that means. So there is sufficient evidence that the average IQ score in affluent communities is higher than the population as a whole at a significance level of 0.05. And again, this will kind of be a good template for you of how to interpret these things in general. So we'll say there is sufficient evidence. Then you fill in what you're talking about here. So that mu, which here is the average IQ score in affluent communities, and then kind of say what you've concluded about it. So we've concluded that it's actually larger than the population as a whole. Questions, comments? Is this making sense what we're doing here? So you're kind of stepping through this very slowly just to kind of think what all the steps are. And when you're doing your homework problems, you can move through this probably more quickly, but just kind of as the first time through here, kind of showing exactly what we're doing and what the goal is here. Okay, well, I think that brings us to the end of chapter 15. Any final questions on hypothesis testing? Yeah.
So
On
on the homework, you want us to write out all those steps?
the homework, do I want you to write out all those steps? Only if it helps you. So if you don't need to, if you can kind of pick out the problem. I mean, it's definitely put your hypotheses. I mean, the questions I think will often say kind of step you through, but definitely say what your hypotheses are. Maybe that's a good question. So what do you sort of have to do in your homeworks? You definitely want to list out what your null and alternative hypotheses are, saying what your level of significance is, And I would even encourage you to identify what the parameter is. So say exactly what mu is in our in the question here. And then of course you definitely want to check your conditions. I mean, then from there on out you sort of do need to put everything. So am I able to use this test? Calculate what the test statistic is, find the p-value, and from there we're sort of needing everything as well. Kind of that whole 4 steps. So we either reject or fail to reject, and then give a good interpretation of what that means. Very good question. All right. Well, in that case, let's see if we can get a little bit of Chapter 16 covered here. We're going to kind of thinking about inference, which is confidence intervals. So thinking about confidence intervals and a hypothesis test sort of in practice. What are some practical issues that we have to deal with when we're thinking about these things? So yeah, so just remember again, we've just now done this, but chapter 14 we talked about confidence intervals. Chapter 15 we talked about hypothesis tests. Now we're going to think about what are some of the practical issues in dealing with these procedures. So the usual conditions that we're going to need to check here, just first make a comment about these conditions. And I'm sorry if I've sort of jumped around on saying what you need to check and what you don't need to check, but here's kind of a good way of what you should always check. So we've said that our 3 conditions in general have been random sample, small enough sample, large enough sample. And it is actually important to check those first 2 even if the population is normal. So even if we have our population being normally distributed, it's still very important that we have a random or representative sample from our population. Remember, if I want to say something about average height of students at Ohio State, I wouldn't want to take all males or all females. That would not be a representative sample of the population. So regardless of what the population looks like, representative sample is very important. And that small enough sample, again, there's some theoretical things there that we do always want to make sure our sample is not too big. So then for the large enough sample, again, you can either go one of 2 ways. So is the population normal? Yes or no. Check or not check. And if it's not normal, then is n at least 40. So kind of this can be kind of your main strategy here for thinking about conditions for hypothesis tests and confidence intervals. We need these 3 things to happen in both of those cases. So instead of throwing these into the end of each chapter, we have a separate set of notes to talk about cautions. Again, remember, we love talking about cautions in this class. So thinking about, first thinking about confidence intervals, kind of what can go wrong when we're constructing confidence intervals. The margin of error, so remember the formula is as our estimate plus or minus the margin, plus or minus the margin of error. So this is x bar plus or minus z star times sigma over the square root of n. And that's my margin of error. And just to comment that sort of theoretically here, that margin of error only covers sampling errors, so that only covers errors that happen in sampling, and doesn't really get at the other forms of bias that we've talked about. It kind of goes back to that, making sure we have a representative sample. So if we have undercoverage of a certain group or non-response or other bias, that's not going to be covered by this procedure. So again, it's always important to minimize those things and just keeping in mind, where did this data come from, and is it data that I want to use to make a statement about my population? Is it good enough data? So again, if we have those errors, we might get bad results, is the point. So we haven't really talked about So let's think about now some cautions for significance tests. We haven't really talked about how to choose your significance level. So we often said alpha equals 0.05, but it could be smaller, it could be larger. So remember that alpha is often 0.05 or 0.10 or 0.01. So kind of those are some usual choices, but again, it could be whatever you want it to be there. And so when we have sort of so to actually choosing alpha means we have to think about sort of the consequences of our decision. So is it a big deal if we reject the null hypothesis? You know, does the null hypothesis represent an assumption that is widely believed? So if there's sort of strong evidence that the null hypothesis is true, we need to find sort of extreme evidence that it's not true, which means that we would need small p-values, which sort of corresponds to a smaller significance level. So just remembering that the p-value remembering what the p-value talks about is that it's the probability that we get values as extreme or more extreme than we did if the null hypothesis were true, and smaller p-values sort of provide stronger evidence for rejecting the null hypothesis. And then, so just a note here that if the problem doesn't, for the purposes of this class, if the problem doesn't say what significance level to use, it's going to be okay to go ahead and use the significance level of 0.05. So if the problem does not say what significance level to use, go ahead and use 0.05. We'll kind of think about issues of choosing alpha. Sort of, we'll push that off for now. So the problem will either say at a significance level of 0.1, do this hypothesis test, or at a significance level of 0.01, or maybe it won't say anything. And in that case, go ahead and use alpha equals 0.05. So really just a lot of terminology here in this chapter, a lot of things to think about. And just so this slide is just kind of pointing out that there is sort of this connection between the confidence level that you choose and the significance level you choose. Those things sort of go hand in hand. And so if you want a high level of confidence for your confidence interval, you're going to choose maybe 99% or something like that. And just the idea that the significance level kind of gets at the same thing. If I want to be more sure in my decision, so if I want to be more certain about rejecting the null hypothesis, I'm going to use a significance value that's smaller. So higher confidence sort of corresponds to a smaller significance level, kind of that same idea. Another caution here about hypothesis tests, which is that if our sample size is really big, then you can get really small p-values, sort of regardless of what the actual difference is. So this idea that something that's statistically significant, so again, rejecting the null hypothesis or failing to reject, that's getting at statistical significance. That's not always going to be practically significant. So what's sort of practically meaningful there? So as a quick example of this, suppose we're back in that first example in chapter 15. We were looking at screen time, and suppose that instead of just looking at Gavin, we looked at lots of children and found that lots and lots of children, so 100,000 children, and found that their average screen time was 6.2. So again, assuming we've checked all our conditions, the test statistic again is going to be z equals 6.2. Again, we're comparing it to that same 6.1 we looked at earlier, divided by sigma over the square root of n, which is now 100,000. And so what we'll get here is that this is equal to 0.01 divided by 0.0083, which is 12.07. So there's my test statistic. So I get a crazy big test statistic, which means that my p-value is going to be pretty much 0. And so that's going to cause me to conclude that there is a statistically significant reason to reject the null hypothesis that the average screen time for these children is not 6.1 hours. But in fact, I've gotten something that's extremely close to 6.1. It's just the fact that the population, that my sample size is so large, has caused that test statistic to be really big and give me a really small p-value. So just this idea that maybe I'll find statistical significance, but think about, is that difference that I'm saying, is that actually meaningful? So if the average screen time is 0.1 hours different, does that really matter? Is that really significant? So that idea of practical significance versus statistical significance, something just to keep in mind there. Okay, maybe the last thing to look at here is to think about, go back again to confidence intervals and think about how sample size affects those confidence intervals. So if you remember back to chapter 14, we found that that the sample size impacts the margin of error, of course. So remember that our confidence interval, again, was x bar plus or minus z star times sigma over the square root of n. Where this, again, is our margin of error, which let's call that m for now. And so what we saw in chapter 14 was that as the sample size gets bigger, your margin, again, you're dividing by a bigger number, so your margin of error gets smaller, and vice versa. So if you're kind of in the planning stage of your study, you might think, well, maybe can I say what my sample size needs to be in order to get a certain margin of error? So remember that's the margin of error here equals z star times sigma over the square root of n. But if there's a certain margin of error that I want to get, so if I want my margin of error to be some number, then I can choose my sample size based on whatever I want that margin of error to be. So just kind of rearranging these formulas to get what my sample size will need to be if I want to get a particular margin of error. So going back to the IQ score example again, we didn't actually look at this in chapter 14, but here I'm giving you the details from it. So if we know that our average adult IQ scores follow this normal distribution, standard deviation 15, take a random sample of 49 adults and find that they have an average of 100, we can find what this 99% confidence interval here is. So again, just taking our sample mean, 49 plus or minus z star, so we want a 99% confidence. So z star, again, remember, needs to equal 2.576. So that's what my confidence interval, that's what I can find it to be. And then, of course, I would want to give an interpretation and all that. We're going to skip that for now. So so again, the margin of error for that confidence interval was 5.52. Remember, I'm adding and subtracting 5.52 to my sample average there to get my confidence interval. So suppose now instead that I'm in the planning stages of this thing, and I want my confidence, my margin of error to be 2 instead of 5.52. I want it to be just 2. So again, I can pick a sample size that will give me that margin of error. So again, the formula was that n is going to be equal to z star times sigma over m, the margin of error, squared. So 99% confidence z star is 2.576. sigma was equal to 15. That's still the same. And if I want my margin of error m to be equal to 2, I can just plug all these things in here. So I want my sample size to be equal to 2.576 times 15 divided by 2 squared. And I don't have this actually written in my notes. I forgot to do that. 2.576 times 15 divided by 2. So that's 19.32 squared, which is 373.26. So if my sample size is 373.26, I'll get the right margin of error. Yeah. So if I want 99% confidence, then my z star is going to have to be 2.576. So sort of the usual confidence levels was 90, 95, or 99%. Yeah. That was those three numbers that I gave you. So 95% is 1.96, 90% is 1.645 or something like that. But z star equals that. Remember that just tells me that if I have my normal distribution with 2.576 and negative 2.576, that means that the area between there is 99%. So that's where that 2.576 comes from. So real quick, just to finish up. So again, if my sample size is that, I'll get the margin of error that I want. Can anybody find me 0.26 of a person? Of course not, right? So we round up and get that n. We need n to be equal to 374. So even though it's closer to 373, if we want our margin of error to be 2 or less, we need to round up there. So always round up if you're asked this kind of a question. All right, I think I'm out of time. We'll finish this up on Friday and get going with Chapter 18. Thanks so much for being here, you guys, despite the crap weather out there. Have a good rest of the day. We'll see you on Friday.